Yeah, I think I can start. So, contextomy, let's debug together. So I already was introduced. This research was done with the help of a fellow researcher, Danny Lisiansky. And I have been working on iOS jailbreaks a long time ago already. Absence, evasion, and more recently also on checkrain. I'm MobileDevice maintainer, and I'm handling research and implementation of threat detections on iOS at Imperium in the research department. And yeah, my fellow researcher, he's independent and is doing random iOS and macOS vulnerability research, and he has also been involved in recent jailbreak development, checkrain. It's not that recent anymore, but yeah. So the agenda for this talk today, first I will give a short introduction covering lockdown-D and device services, and then go over a few past vulnerabilities from that area. Then I will cover the discovery and the research of the actual vulnerability that I'm presenting about today, and later the exploitation, and also a short section about the vulnerability disclosure and the fix, and of course some Q&A in the end. So let's get right into it. So on iOS there's a daemon running. It's called lockdown-D, and that's the main service daemon. It's always running. It handles device pairing between the pairing between device and the host computer. It provides device information. It's responsible for service startup. Originally, the implementation was just USB only, and later Wi-Fi support was added. Services on iOS have multiple different purposes. For example, backup, file transfer, app and profile management, system logs, diagnostics, and if you mount a developer disk image, you can also get debugging and instrumentation capabilities. Wireless connection support has been available for quite some time already. Starting with iOS 5, and all the services, the connections, they require SSL, which is not the case on like if it goes over the wire. Starting with iOS 11, Apple introduced wireless debugging, and that's what this vulnerability is about. Some past vulnerabilities, just to get a little history and background about a few things that me and also Danny discovered over the years. So one of them is a directory traversal, which is actually leveraging two services to pull it off. Basically, the file, the AFC service, which is short for Apple File Conduit, allows, or allowed in the past, not anymore, to create symlinks. But it's a jailed environment. However, you could still point a symlink to whatever location you want. If you then put a symlink at a specific location and create a crafted backup that restores to that location, and you then restore that backup, it would write to the location that the link points to instead of the actual directory. That was used in the Absence 2 jailbreak back for iOS 5.1, quite a long time ago. Backup agent, so the backup service itself also had a directory traversal, because it has quite some nice features. It allows to create, backup and restore symlinks. And basically, it's a very similar idea. You need to have a location that you have access to, and For the backup service, there are certain paths that are allowed, so you cannot just put it anywhere. But basically, one of these backup domains, you can just add a symlink and have it point to the location that you want to write to. And then you can just, like in the same order, like the symlink, then you add the files that you want with the pointing to a directory, and then you add like additional entries for that specific directory. And then when you restore the backup, it will create the files at the location that the link to points to instead. That was used in the evasion jailbreak, iOS 6. Another vulnerability, which actually got a CVE, but it's very simple. So lockdown-D has some code that runs when it started, and it's performing some cleanup tasks and some migration tasks and some checks. And one of these tasks was to change the permissions of a certain file. And but there are no checks whatsoever. So basically, using the vulnerability that I mentioned before, the directory traversal, with a symlink in the backup, you could basically restore your crafted backup and then have lockdown-D basically change the permissions when you restart it. And now it's like always running, but if you want to restart it, you just have to make it crash. So basically send a malformed request to it, and then it just crashes. Nowadays, it's doing a lot more sanity checks, so it's not that easy to crash it anymore, but I think there are still some ways to do it. But anyway, so yeah, you just had to create this fixed path with a symlink, and then write that specific file name, the time zone file name, to the backup, just as a symlink pointing to whatever file you wanted to change. And the interesting thing here is, if I remember correctly, you can even make it point to a different file system. Yeah, so that was also used in the evasion jailbreak for iOS 6. A more recent vulnerability is called, or was named, Launchdown by Danny. And so basically, when you mounted a developer disk image, the process that handles the mounting procedure will send a notification, and lockdown-D and the installation daemon install-D, they will observe or listen for this notification, and based on the path that is in that notification, it will load some resources. And for lockdown-D, this technically means it checks if there are any additional agents on the disk image, so it can add additional services like the backup, like the debugging service or instruments. So the thing is, you can spoof the notification from a third-party app and just specify your own path, and that way you can fool lockdown-D to load custom agents, which are defined by a property list file that has like all the arguments and well, the actual command and like what user you want to run it as. So it's being handed over to launchctl as a job, and then it just runs whatever command you want. That was fixed in iOS 12.3, and some more information is available on Danny's GitHub repository. You will get the slides later, I think, so you don't have to like write down the link because it's quite long. Yeah, so let's get into the discovery and the research of the c0ntextomy vulnerability. So, starting with iOS 13, even for connections that go over the wire, over USB, Apple changed it so that the service communication has to use SSL, encrypted communication. Wireless connections had that already, as I mentioned before, with iOS 5. And so it happened that someone posted a bug report on GitHub for the iMobileDevice project that the debug server communication failed over USB. And it turns out that when the service is started, it performs an SSL handshake, and then it just drops to plain text. Like, it's not shutting down the session at all. It's just straight drops down to plain text. And at that time, the iMobileDevice couldn't handle network connections yet. And we basically were like, wait, so if that's happening over USB, it certainly must be happening over Wi-Fi as well. So we did some network sniffing, and like very quickly you could see that it's all plain text. So of course then the question is, can this be exploited somehow? Can we do something with it? But also we wanted to fix the iMobileDevice because like people kept complaining, and obviously you want to fix it at some point. So we did quite some research on this topic because we wanted to understand what is actually happening here, and because the SSL connections were actually handled correctly, according to our understanding at least. And we did some experimenting where we basically said, okay, what if we don't do the switch to SSL mode and see what happens? But then the debug server would be like, nah, this doesn't work, and then just drops the connection. And if you look at like the actual communication itself, USB or network, you can see that it actually does the handshake. So something must be there, which is not quite right. We also tested like shutting down the SSL session, but that also doesn't work because it creates additional traffic, which is not expected on the other hand. Yeah, as I mentioned, so the handshake, after the handshake, it just has to be completely ignored. And yeah, this sounds to be like some architectural problem here. Yeah, so fixing the iMobileDevice wasn't that hard actually, but basically we had to break the clean implementation that we had to fix this. And there were a few people that suggested some changes, and in the end it was just a function that we had to add to basically say, okay, let's just disable SSL, but without like shutting down the session, just stop sending any packets. And then for the debug service implementation in the iMobileDevice, we added a call to that function, so it can continue to talk in plain text after the service was started. So let's understand the underlying issue, because I think it's still not quite clear why this happens. And so if you look at macOS, the code that handles service startup and like also the communication with lockdown-D and everything is implemented in the MobileDevice.framework, and like all the API that is required to handle all these things, and that's obviously used by Xcode and all the other tools. And basically, after a service is started, lockdown-D sends back a port number, and it has, I mean, it's a dictionary which has a port number, but also has a property enable service SSL, which is either true or false, obviously depending on the iOS version, because starting with iOS 13, like it's always true. So if you look at the code, or well, the disassembly of MobileDevice.framework, you can see that it performs the handshake, and I mean you can see it on like the network traffic as well. But if you look at the code, you can see that it checks the return value and then decides to do the handshake or not. So that seems to be fine, and this is aligned with what's happening in the iMobileDevice. So But what happens on the what happens next on the device side? So lockdown D handles the handshake for the switch to SSL mode for the service connection, and it will then launch the service process. And every process that's launched by lockdown D has to check in. And usually after that, it will basically get the socket file descriptor, and it will get the secure context, so it can continue to use the encrypted communication channel to hand it over, because it's a different process. However, if you look at the debug server implementation, you can see that it never calls lockdown get secure context, which is the function that would allow it to use the encrypted communication. So it turns out it doesn't even expect it to be encrypted. On the host side, what happens is first you have to understand how things are implemented with Xcode, because the developer tools are basically implemented outside of MobileDevice.framework, and the service startup is initiated by Xcode in a plugin called IDE iOS Support Core. And basically what happens is it uses the MobileDevice.framework code to start the service and wait for the reply. It does the handshake and everything for us. And then once it has the successful service startup, it will take the socket file descriptor number and then pass it to LLDB RPC server, which is the process that's responsible for all the communication between the debug server on the device and the Xcode debugging session. But it's pretty much unaware of the missing SSL, and LLDB server is just using the connection. But then again, debug server isn't expecting it, so from implementation standpoint, at this time, you could say it seems to be okay, but still we have the problem that it actually should be encrypted, like the other services. So a small summary of this, we call it design flaw because that's what we think what it is, an architectural design flaw. And we think that it evolved over time because initially there was no need for SSL because it was just USB only, and basically it was okay to expose the raw file descriptor and then just use it externally because technically it wouldn't make a difference anyway. If it doesn't have to be encrypted, you can just pass it, and who cares? It just works, and why would we change it? Or they. But then Apple added wireless development to Xcode a few years later, and since MobileDevice.framework or the code in it handles the SSL handshake, but on the same at the same time, it still allows to get the raw file descriptor, and that's what's happening, and it's passing the file descriptor to Xcode. So basically, this kind of breaks the abstraction of the service communication code from the standpoint of the consumer application. And unlike the iMobile device, where we have a clear hierarchy of how things are implemented and how all the communication is working. Like it just doesn't make sense, at least for us, to implement it this way. So that's why we think it's kind of like an architectural design flaw. Maybe it was just easier to do it that way, but then in the beginning there was no Wi-Fi debugging, and it wasn't really a problem. But well, now it became a problem. So let's get into exploitation. So is this actually exploitable somehow? It is restricted by a few things, because one thing is that the attacker needs to be in the same network, and the attacker also needs to be able to redirect and manipulate the network traffic to get any use from this vulnerability. And the victim also has to start a wireless debugging session, because otherwise you wouldn't have access to it. So basically we ourselves came up with a kind of a predefined scenario that makes this kind of possible. So it's an intruded local network inside a company that's developing like an AR or fitness application, and they use wireless debugging to debug it. So just assuming that we have that, technically we should be able to exploit this. But there are a few things that we need to take into account here. So the first thing is we need to gain control over the debug session. And to do that, we need to redirect the network traffic, which is usually done with an ARP spoofing attack. So we can redirect it to a machine that we control, and then we basically do a man-in-the-middle attack to take over the session and like manipulate everything. However, we cannot predict the port of the connection that debug server has been started or debug server is communicating on, because every time a service is started, which is pretty normal, like the port that it listens on is assigned randomly, and yes, and also the actual service startup sequence, like when you tell lockdown hey, start this service for me, and you have to switch to SSL mode as well for this specific part of the communication. So you cannot just see the port if you sniff the network traffic. It's encrypted, so you wouldn't get the port number right away. Yeah, basically this means we have to look at all the TCP sessions that are going between the victim computer and the victim iOS device, and then pick the right one. Which is not that hard. So basically this is a GDB remote session. That's the protocol that you can see in the traffic. And it basically has a very easily identifiable handshake, like a very clear pattern that you can just listen for. And once you see that, you know, oh, this is a debug session, so this must be the right one. However, if you just try to manipulate it just like right away when you detect this, things will break, because it has quite some communication in the beginning, setting up a few things and like some breakpoints and stuff. And so we have to wait a specific for a specific event. So we know that this session setup is complete, and we can basically begin. So what's the right point in time to do that? And I mean, the idea is very simple. We just look how what Xcode is doing, or when Xcode basically thinks that the app has been started and debug session is configured and everything's fine. So when it configures the debug session, it basically sets up an async process profiling feature, which will send telemetry data about the process, about memory and process, CPU usage and things. And that it sends profiling packets every now and then. And once the host starts to receive this packet, like if Xcode receives this packet, then it will present the debugging UI, and you can see like all things moving like this, graphs and things. So so for us, it means basically if we see this profiling packet coming over the connection, then we know we can start. So what we want to do now is we want to basically add a second client to the debug session, which is technically not the way it should be. Like basically you already have the connection, you just add a second client. That's not how it works, but in under normal circumstances. But the thing is, we want to keep Xcode unaware of the connection hijack, and so the victim doesn't notice that something weird is going on. And this is basically how we do it. So we wait for the profiling packet, and then we save it so we can replay it later. But we don't relay it to the host. Instead, we send a process interrupt packet to make the process stop. Like, so tell basically debug server, stop the process. like pause the process, not kill it, pause the process execution. And this is because LLDB expects that the process is stopped when it tries to connect. And then we separate the original session and start replaying the profile packets on that connection. So we basically send the profile packets to Xcode. So it just thinks everything's fine, the app is running, it's all good. And then the attacker joins the party, basically. We are in control of the control session, of the debug session, and the process is stopped. So how do we add a new client to it? So let's just try. So start LLDB, GDB remote, IP address, and the port number that we figured out from the connection, because we're sniffing the traffic so we can see on what port number it's on. But yeah, it like errors out. It says failed to get reply to handshake packet, and it doesn't work because, well, it actually wants to do like this debug session setup sequence. So sending a bunch of packets and configure like compression and all kinds of things. And so the idea now was, so what if we don't relay the session init packets to debug server and reply to the client with the expected reply? So basically fool LDB that we're like the remote end is replying to it. I mean, we tried that and that works. And yeah, that basically means now we have full session takeover in place with a working LDB shell. We can run all the commands and interact with the process, run custom code, whatever you want. So this kind of was a bit impractical. So we did some more research to find a better way to add the second client. And we found a solution. So basically, the GDB remote command is implemented as a process connect plugin. So you can basically do process connect -p GDB remote, and it actually takes arguments, and you can basically specify a file descriptor, so that makes it way easier. So we don't have to deal with this, like sending like fake replies back to LLDB, because you can just tell it, hey, use this file descriptor, and then it will just just take over the connection for us. So this allowed us to implement reverse LLDB client, basically, that accepts connections, and once it gets a connection, it will pass the socket file descriptor straight to LLDB. So that's a very clean approach. So what we now have is technically remote code execution, even though the circumstances are a bit limited because of that the attacker has to be in the privileged network position. But it's not an impossible scenario. So we are now in control of the LLDB session, and LLDB has nice features like the expression command, and you can basically use that to run code in the context of the process. There's no code signing and whatsoever. You can just run whatever you want. And then we actually over-engineered a POC that ended up being a complete tool set, like with plugins or modules that allow to exfiltrate data from the device, or like, play some audio or so we created a payload that we used to bootstrap LLDB that runs a new thread using the expression feature of LLDB. It then connects back to our exfiltration server. That's just the process that listens for incoming connections from all the modules that we created. First for the initial like bootstrapping, and then it will execute additional like the modules as additional payloads. transformed to shellcode. So yeah, this is how the remote execution basically works in the POC. Basically proves that it's a realistic scenario that allows to get data from the device. Now the question obviously is it really that critical? Because it's still a development environment, so usually there's probably not that much critical data on the device. But what you could do basically is you could dump like the actual app itself. You can like extract the complete application container. You can basically steal the application without actually grabbing it from the developer's computer. You just take it from the device. I mean, there are certainly other ways to do that, but just as an example. Yeah, so a little bit about vulnerability disclosure and the actual fix of this problem. So the disclosure timeline, basically it took quite some time to do all the research, but also this is because we kind of did that in our free time. So in June 2019, we discovered that based on the bug report from the MobileDevice project. And then we took the time to research everything and create a nice POC and like a write-up and to create an actual advisory. And then we sent that to Apple, which actually happened to be 2 years ago when Nullcon was happening in March 2020, where I also was attending. So, but that's just a coincidence. And now I'm presenting the research again at Nullcon, which is quite funny, I think. Yeah, so Apple replied and they said, hey, you cannot just, disclose that after 90 days. We need more time. And they said it takes time until later this summer, and they kindly asked. And yeah, we said it's okay. Then, surprisingly, in August, they told us, okay, the new Xcode beta versions, they have a fix, and so we can have a look if the problem is solved or not, which we obviously did. And yeah, well, we then found a downgrade attack that bypasses the new patch that Apple introduced here, affecting iOS 13.6 and 13.7. So downgrade attack, like what's going on here? So Apple said it's fixed with Xcode 12 beta 3, and of course we just had to look what does it actually mean, because it's like kind of an architectural change that you have to make. And that's why they also asked for more time, because it wasn't a simple thing to do. It's not like a one-liner that you need for the fix. So we look at the developer disk images, because that's where the changes have to be applied, since the debug service is, at least for the device side, the debug service is not coming with the stock iOS software, but with the developer disk image. Everything that is below 13.6, there was no change whatsoever, no mitigations. But yeah, it's also like an older iOS version, so it's somehow understandable. The developer disk image for 13.6 and 14, and 13.7 as well. They had new secure service variants that actually use secure communication. But also they still had the older service name. So basically they added a new service, and the old one you could still use. And starting with the next beta version, which just came out a few days later when we looked at it, the iOS 14.1, they removed the old variant. So you always have to use the encrypted one, starting with iOS 14. So that means that iOS 13.6 and 13.7 they stayed vulnerable to a downgrade attack. And yeah, Apple basically told us that only iOS 14 and later will be fully addressed regarding this issue. Yeah, and that's what they did. So the downgrade attack is not that complicated actually, because the way it was, the changes were introduced into Xcode is because they have a fallback mechanism. Basically, if the secure service cannot be started, it will fall back and try the insecure one. And so basically, if you have a man in the middle position and you can look at the packets, you could find, it's an encrypted start service packet that you're dealing with. But if you have some heuristics or just look at the size, you have a very high chance to find the actual service startup packet, and then you just drop the connection. And then what happens is Xcode thinks, so the service startup didn't work. It reports an error back, and then it will just fall back and say, okay, let's start the insecure one instead, because that's how it's implemented. And then, we again can party because, but only for the older versions. But still, was interesting to follow up on this matter. So what did Apple actually do? I already kind of gave it away. So they added secure service variants for the debugging and the instruments services, and I think all the others that didn't have it as well. But some of them already were using proper SSL communication. So this basically creates a tunnel for the encrypted communication, and the device side, so the debug server was updated to reflect that change. That actually it's like a tunnel, so it will decrypt the traffic and then pass the decrypted traffic to debug server technically. And on the other side, like the socket file descriptor of the other tunnel endpoint on the host side will be passed to LLDB RPC server, so it can now transparently communicate over a secure connection. So this is where the architectural design flaw was actually mitigated. And this is more or less how we have it implemented in libiMobileDevice. If it switches to SSL, you just handle everything, and then you just pass the encrypted communication endpoint to the consumer, and then it just transparently just uses that connection, whether it's encrypted or not. So we have now the full disclosure timeline. It's just the same as before, only that, as I mentioned, Apple told us in September that they will not address it in other versions except 14 and WatchOS 7. So only those, and later will be addressed. And September 16 is the date when Apple released Xcode 12. That had all the patches that we could already see in the beta versions. And that's the CVE number that we got for the disclosure. So that's basically it. And so actually I thought about doing a live demo of this thing, but it's quite complex to set it up. I would need a second machine, and then it turned out like my older MacBook already had like everything updated, so I didn't even have the right Xcode version. But back at the time when we did the submission, we were thinking about, just submitting this bug to the Pony Awards for like most epic fail, just, nominate ourselves. But then we forgot 2 times to do that. And Danny, he created a short video clip regarding this matter. So, and that's what I want to play now. So sorry for not having a demo. I hope you still understand how this whole thing works. We have the whole POC, all the code and all the documentation, the advisory, and very verbose README that explains all the details of this vulnerability. On the GitHub repository, I will show the link right away. It's already public for some time, but we never had a chance to present it at the conference because all this pandemic that happened right after the last Nullcon where I was at. And this was our chance to present it. Unfortunately, Danny couldn't make it here, so because he has lots of personal projects going on. So yeah, maybe another time. So yeah, that's what I wanted to show you. So I hope the audio is okay. Let's see. Okay. I hope you enjoyed.
It is now possible to develop and debug on your device over Wi-Fi, and we call this wireless development.
We found a loophole.
Yeah.
Yeah. All right. Yeah, that was my presentation. I hope you enjoyed it. Let me know if you have any questions.
Hello. Any questions? You have the mic.
So is this vulnerability have anything to do with the connection with the car, like Apple wireless CarPlay or those kind of things as well? Or it was just between the MacBook and the Apple iPhone device, Apple devices?
I'm not sure if I heard everything correctly. So you're asking if this is only between like Xcode, macOS, and the device, or
yeah.
So you want to know if it's like if the vulnerability is affecting other areas?
Yeah, it was Apple CarPlay, the wireless CarPlay in your car. That's where you connect with your car. So was also that this module was used in that functionality as well? I
didn't really hear you that well.
Can you please repeat? We didn't get you.
Yeah, so I'm asking the Apple CarPlay, which allows mobile phone device to connect over the wireless network.
Yes.
Earlier it was over USB. So does that thing, does this particular disclosure you mentioned, was that impacting that functionality as well, or is what it was just Xcode that was used between the iPhone, like the mobile device, and other MacBook or other Mac devices?
Yeah, it's very specific to Xcode and the wireless development. It doesn't affect any other areas. So it basically means if you don't do wireless development, there's nothing to fear about. Is that what you wanted to know? Okay.
So so when you connect with the car, so it's basically also the wireless. So I'm not sure if that was the Xcode utility was used there or not.
Oh, like if you use a different platform?
Actually, he's asking if there are other platforms like Apple CarPlay.
I mean, well, technically yes, because it's not unencrypted because you're using Xcode or macOS. It's unencrypted because it's implemented that way. And we had the same issue with MobileDevice, where we basically had to break our abstraction to get it to work again over USB, where it was also broken, which is fixed as well now, of course, because it's the same thing, just a different connection. So yeah, you can still exploit it even from other platforms, but yeah, you would have to do like wireless development, and yeah, I don't know if it's that readily usable, but technically it's possible, yes.
Okay, thank you.
Yeah.
Any other questions? Thank you, Bassen.
Thank you.